Alright, so today what I'm going to do is Chapter 2, Problem 67. That was a problem that students said that they wanted to see solved on a video, and so to give you an idea of what that problem is, I'll read it off for you really quickly. It says a 200 kilogram weather rocket is loaded with 100 kilograms of fuel and fired straight up. It accelerates upward at 30 meters per second squared for 30 seconds and runs out of fuel. Ignore any air resistance effects. And the first thing they want to know is, what is the rocket's maximum altitude? Maximum altitude is basically the maximum height. And so what I've done is what every one of you should have already done, which is draw a diagram. So I diagrammed the situation here and I broke it down into three parts. The first part is when it's accelerating at 30 meters per second squared. And so as it's accelerating positively in 30 meters per second squared, it obviously accelerates upward. It's speeding up, and eventually the fuel runs out, and the rocket then stops accelerating in the positive direction and then begins to go into free fall, where its acceleration is negative 9.8 meters per second squared. After it's negative 9.8 meters per second squared, then the problem just continues, continues to go. I could have broken this up into two parts, one where the acceleration, the positive acceleration is happening, and then one where the negative acceleration is happening. However, I decided against that because the first part of the problem asked where the maximum height is, which would happen, the maximum height would happen when the speed of the rocket is at 0 at its maximum point. So when it's at the maximum point, the speed of the rocket is 0, and at that point on, then it just speeds up on its way down as it makes its way down. Alright, so let's start with part A. So part A is asking, what is the rocket's maximum altitude? So to find the rocket's maximum altitude, what I'm going to do is I'm going to find how far it travels at the first part when its acceleration is 30 meters per second squared. And then I'm going to find out how far it travels once the fuel cuts out and its acceleration is negative 9.8 meters per second squared. So I'm just going to do that in two parts, and then I'm going to add those two parts together. So for the first part, let's start with the first part. So for the first part, I'm going to make my VOVAT. I know that my initial velocity is going to be 0 because the rocket starts from rest. I know from the problem they told me it accelerates at 30 meters per second squared. And I know that this happens for a time of 30 seconds. So I can find my displacement. That's what I want to find. So in order to find my displacement, I'll probably use this one. D equals V naught T plus 1/2 AT squared. So my displacement, that's the first displacement, all of this is just 0 because it starts at rest, plus 1/2 times the acceleration. I'm going to use, the acceleration is 30 meters per second squared, and the time it takes is 30 seconds squared. So if you calculate this, you get that D1 is 30 squared times 30 times 1/2, which is 13,500 meters. So I got 13,500 meters. But that's just for part 1. So for part 2, I'm going to make a new VOVAT because the acceleration has changed. So this VOVAT I got a new initial velocity. My acceleration is now negative. I'm going to use negative 10 just to make the math a little easier. I'm trying to find the displacement. I don't know how long it happened for, but I know that the final velocity at the peak of the rocket's path is going to be 0, because it's going to be 0 before it starts to travel downward. So it stops at rest for a brief moment. So to solve this, I need 3 things to solve a VOVAT, and so I still need one more bit of information, and I think the best place to get that one more bit of information is the initial velocity, which I can find because it's going to be the final velocity of the rocket just before its fuel gets cut off. So to find that final velocity of the rocket, I'll create, so this is all from here. I'm going to find out that by using this equation here, V equals V naught plus AT, from the previous problem, because that's going to tell me the final velocity. So the final velocity here again is the initial velocity that I'm going to find over there. So my final velocity, I don't know. My initial velocity was 0. I accelerated, the rocket accelerated in part 1 at 30 meters per second squared, and it did that for 30 seconds. If you calculate that, that's going to give you a final velocity of 900 meters per second. Boom! So that 900 meters per second is the initial velocity for part 2, because the velocity at which part 1 ends would be the initial velocity at which part 2 begins. Alright. So now that I know that my initial velocity is 900 meters per second, I can find out the displacement for part 2. And so to find out the displacement for part 2, I know my initial velocity, I know my final velocity, I know my acceleration. If I know those 3 things, I can use V squared equals V naught squared plus 2AD to find out the displacement at which the second part travels. So to isolate all this is going to be V squared minus V naught squared equals 2AD, which is V squared minus V naught squared divided by 2A, which is the displacement. And now that I know all that, I know my final velocity. I can plug things in as 0 squared minus the initial velocity is 900 meters per second, but all that is going to be squared, divided by 2 times the acceleration, which is -10. Now that I know all that, this is displacement 2. This is the second part of the displacement. Again, going over to this diagram here, this is D1, which I know is 13,500 meters. And then D2 is going to be what I'm going to solve for right here. So that's what I'm going to find right there. Alright, let's calculate it. So D2 is -900 squared divided by -10 times 2, which ends up being 40,500. But now that I got all that, I'm looking for the total displacement, the total distance traveled by the rocket, which is D max. And hopefully you can see that D max is just D1 added to D2. So D1 plus D2 equals D max. Let me write that out. D1 plus D2 equals D max. So I can plug all that stuff in. D1 I found in this part right here is 13,500 meters plus D2, which is the 40,500 meters. So it's going to be 40,500 meters equals D max. So that means that D max then is 13,500 plus 40,500 500, which is about 54,000 meters. You could say 54 kilometers, or if you use 9.8, you could have gotten something a little bit different from that. But regardless, it ends up being about the same, which is 54,000 meters, and that's the displacement there. Let me make that 5 a little bit different because that might be a little confusing. Here we go. 54,000 meters is what I think is the maximum height. Next up, I'm going to find out part B, which is how long is the rocket in the air? All right. So how long is the rocket in the air? That's part B. So for part B, how long is the rocket in the air? I'm going to go back to my diagram. So I'll delete a little bit of this. How long is the rocket in the air? Well, I know for the first part, the first section, it's there for 30 seconds. It should be seconds. And then when it starts in free fall, I don't know how long it is in the first part to where it stops accelerating at 30 meters per second squared and starts to accelerate at negative 10 meters per second squared. And I don't know for how long it accelerates on its way down. You could solve the second part of this, the second and third part of this problem with a quadratic, but because I solved the previous problem with a quadratic that I did a video of a couple days ago, I'm going to solve this one using a different method that I'll show you right now. Alright, so okay, the first thing I'm going to do is use my initial VOVAT here because I'm going to solve for time. So I'm going to use this VOVAT again for part 2. I know for part 1. I know for part 1 that the object travels for 30 seconds. So it accelerates at 30 meters per second squared for 30 seconds. So whatever time I find out here, I just need to add that 30 seconds to it at the end. Alright, so this is the VOVAT for part 2 when it starts to accelerate at negative 10 meters per second squared over here. So once it starts to accelerate like that, let's see if I can do this. Yep. So once it starts to accelerate like that, let's see. I found out previously that this was 900 meters per second. And so now I'm just trying to find out the time at which that happens at. So I think again I'm going to use v equals v naught plus at, and I'm going to isolate time. So it's going to be v minus v naught equals at. Divide both sides by a, so it's going to be v minus v naught over a equals the time. And plugging everything in, it's going to give me at the final velocity is 0 minus the initial velocity, which is 900 meters per second, divided by the acceleration, which is time. So if I divide those things, I get negative 90. Sorry, that should be a negative right there, which cancels. And that gives me a positive 90 seconds right there. So that's positive 90 seconds. That's the second time, right? So I got the 30 seconds plus this 90 seconds, and then I don't know how long it's going to take to move its way down. So let's figure that out for part C. Let's do part C right here. So this is going to be part C. I got another VOVAT I'm going to make. So for part C, I'm going to call my initial point right when part 2 ends. That's going to be my initial point. And my final point is right before it hits the ground. The rocket hits the ground. So if my initial point is right when part 2 ends, I know that that would be initial velocity of 0, right? Because where part 2 ends, the final velocity is 0, which is at the peak, and I know at the peak the velocity is 0, so that means my initial velocity is 0 then for the way I've defined this part to be. Alright, final velocity, I don't know. My acceleration I know is negative 10 meters per second squared. My displacement I do know, because that would be the maximum displacement, which I found in part A, which is 54,000 meters. And so I can find out the time it takes to get this, to do this. So let's see, I'm going to use, what should I use? Let's use d equals v naught t plus 1/2 at squared. My displacement is going to be negative, right? Because it's going down, because the object is going down, so it's negative 54,000 meters. So it's negative 54,000 meters equals 0, because the initial velocity is 0. So 0 times t is 0, plus 1/2 times negative 10 times the time it takes, which is what I'm looking for, squared. So this is going to be negative 54,000 equals negative 5t squared. Divide both sides by negative 5. And the negative cancels out. So 54,000 divided by negative 5 is 10,800 equals t squared. And I can take the square root of both sides. And that gives me about 104 seconds. Alright, so this is T3 though. This is the last part. So it takes, let's go over here. It takes 30 seconds to go up at when it was traveling at 30 meters per second squared. Then I found out that it takes 90 seconds to make its way up before it becomes before the rocket goes to rest. Once the rocket is at rest, it takes 104 seconds to make its way back down. So all I need to do now is add up all of those times. So T1 plus T2 plus T3 is going to equal the total time it takes. So T1 was 30 seconds, plus T2, which ended up being 90 seconds, plus T3, which is 104 seconds, and that's going to be the total time. So the total time is, add those up, 224 seconds. And that's part B. So lastly, in part C, a little more qualitative question. It asks, draw a velocity time graph for the rocket from liftoff until it reaches, until it hits the ground. So velocity versus time graph of the rocket would look something like this. I know that, so let's look at this really quickly. I know at the first part it's accelerating at 30 meters per second squared, and then the rocket cuts off while it's still moving up and starts to accelerate at negative 10 meters per second squared. And it does so even as it stops here and moves down. So if I know that, I can make my velocity versus time graph like this. So it starts at rest, it accelerates at 30 meters per second squared, and then it cuts off at some point, and then while it's still traveling in the positive direction, it then accelerates at negative 10 meters per second squared, which is going to have a more shallow slope than the 30 meter per second squared slope that I have here. But it's still going to travel in the positive direction. It travels in the positive direction, reaches 0, and then moves in the negative direction until we get something like that. So that's what my graph, my velocity versus time graph would look like. That is that problem. Hopefully that helped you. And if you have any questions, come see me. All right. Thank you. And see you later. Bye.